fractions yet?
They're fun.
Good.
Do partial fractions, but I'm frustrated with 7.3 stuff.
You do partial fractions when you're frustrated with trig
Well,
sub.
like,
That's okay.
Move on.
Move on. So the trig sub, it's a trig sub, right? You do a substitution, you get a trig integral. So the substitution part is okay, just the trig integral part isn't. Draw a triangle, kind of the same.
Yeah. Triangles are good.
Good. So you're all set. Are we okay? Any questions on anything? On anything? Okay, if not, I'm going to move on. So, 7.4. So we have 4 techniques of integration. Actually 5. Substitution, which is way back in chapter 5. Integration by parts. Trig. Not the technique. Trig. Power of trig. Trig sub. And then partial fractions. Okay. So we're done with the different techniques. And then 7.5 is essentially it's a section with a bunch of different integrals just put in there without telling you what technique to use. I consider 7.5 more practice problems. 7.6 is a section on basically using tables, which to me isn't very enlightening. So it's like, here's an integral of this form. If you look in the back of your book, there's like a table of like 130 integrals. So basically look at your integral, see what form it is, go back and look at the table and kind of use that. So I think all of you can use a table just fine. So now I'm going to cover 7.6. So the next section is 7.7, which kind of goes back to what we first started doing, the very first thing in this class. Wasn't panicking. Okay. So the first thing we did in this class was what? We approximated areas underneath the curve using rectangles, right? Remember doing that? So those are Riemann sums, right? And so 7.7, we're basically doing that again. We're using basically some approximation techniques to approximate values of the definite interval. Okay? And so, you know, when I was typing up these notes a while ago, the question is, why are we doing this? Well, kind of 2 ways, 2 reasons. So let me first start by saying this is 7.7. I actually like my notes for this section a lot, so I think it's all in front of you. So I don't know if you can copy anything really other than the examples. So the idea here is, again, we're going to approximate the value of a definite interval. Okay, and we already did that in section 5.1. So in 5.1, we had basically 2 techniques that we talked about, right? We had something called R sub n and L sub n. What were they?
Left end point and right end point?
Yeah, so this is the right endpoint approximation. Using rectangles, right? So the n stands for the number of rectangles you have. And then, so this is the left endpoint approximation. With n rectangles. Okay? So if you go back, if I kind of listed what we had before, right? We have L sub n is this sum. So basically take the height of each function evaluated at the left endpoints, multiply that by delta x. Delta x, remember, was the width of your rectangle. So that's the width of your subinterval. How do you calculate delta x? Remember, b minus a over n. Okay, so again, this we've done before. And so kind of as a picture, right? So here's an example of left endpoint approximation with 4 rectangles. So if you notice, the height of the rectangles are evaluated at the left endpoint. So the left endpoint's x of 0, x of 1, x of 2, x of 3. And so you look at the height of the rectangles evaluated at the left endpoint. And so for this particular function, again, how's the approximation to the actual area that I want to get? Remember, the actual area is the area underneath the curve, right? Is it exactly what I want?
No.
Yes or no? No, because there's this little gap that I don't get, and there's this little bit of extra that I get that I don't want, right? The right endpoint approximation, same thing. If I evaluate my height at the right endpoints, I get, again, these 4 rectangles. And again, look at this approximation. Is that good or bad? Kind of good, a little bad, right? It's not the exact area because, again, we have a little bit of extra here, and then the rectangles don't give us the gaps there, right? So, you know, it's probably not the greatest. So, again, there are, you know, and one way to kind of get a better approximation, if you remember, is to increase the number of rectangles, right? So if I have more than 4 rectangles, if I increase the number to 6 or 8 or 20,000, it's going to be a pain to calculate, okay? The approximation is going to get bigger and bigger. And of course, if you tack on a limit to that, that's the definition of our definite integral, okay? So all of this, these 2 things we've seen before, right? Okay, the left endpoint and the right endpoint, okay? So, again, why are we doing this again? Why are we approximating when we could just use the FTC to evaluate our definite integrals? So, why? Tell me why. Why are we doing this?
For when it doesn't work.
What doesn't work?
FTC.
Okay, so FTC doesn't always work. Why not? So when you say FTC doesn't always work, what do you mean? So what does FTC require? Specifically, when you're evaluating definite integrals, what part of FTC are we using? Part 1 or part 2? 2. So FTC 2 says this: the integral f of x from a to b of f of x dx is big F of b minus big F of a, right? So what is big F? What have we been finding all along in this class? What was sections 7.1 through 7.4 about? Finding what? Area.
Antiderivatives.
Okay, we were finding these big F's, right? So this big F is called an antiderivative, and antiderivatives are not unique. Is an antiderivative of little f. Okay, so FTC part 2 only works when you can what?
Antidifferential.
Find an antiderivative, right? So that's what 7.1, 7.2, 7.3, 7.4, 5.5 was all about, was we were finding our antiderivatives for all of our various functions so that you can apply the FTC part 2 to it to find your area underneath the curve, etc. Right? So for many functions you can't find an antiderivative. Can you find an antiderivative for any function? Hint.
No.
No. Hint. No. Why not? Because if we could, why are we doing this, right? So one reason why we are doing this, when you say FTC doesn't work, FTC actually always works, assuming that you can find an antiderivative. It's this thing right here that might not always you might not always be able to find it. So this might not exist, or in most cases, it's going to be hard to find. Okay. So I'm going to put this in quotes. FTC actually always works, but in order for FTC to work, you need to be able to find an antiderivative for it to work. Does that make sense? Okay. Well, what's a function where you can't find a nice antiderivative?
E to the x squared.
E to the x squared. Right? Imagine trying to do this. If I gave you this question on a test and I ask you, okay, solve this using FTC, you won't be able to do it. Or you would try to do it, get an answer, and it would be wrong. Okay. It's because this function does not have a nice elementary antiderivative. Which means what? The derivative of some function is e to the x squared. It's actually, you can't find one. Okay. So again, if you try to evaluate this, right, you do a u sub, that doesn't work. Like u be x squared, okay, so that x won't cancel out when you take the derivative of that, okay? Certainly it's not a trig sub problem. Integration by parts, you can try that, but again, it's not going to work. What other techniques can we use? Trig sub? Certainly not trig sub, and there's no fractions to do a partial fraction on this, right? So in this particular case, again, e to the x squared is a pretty nice looking function, right? It's nothing special, other than the fact that there isn't a nice antiderivative. So, but what is this asking you? The integral from 0 to 1 of this function is to find what?
The area beneath the curve.
Yeah, of e to the x squared, right? What does e to the x squared look like? Do you have a calculator? It looks like a parabola opening up, right? And then at 0, its intersect is 1, right? So you're saying maybe something like this? Okay. And so the integral from 0 to 1 is essentially that area, right? What is that area? It's some finite number. Okay? We can find areas underneath actual parabolas, so it seems like we can find an exact value for that area. Turns out that it's actually quite difficult to do that, which is kind of interesting. Why? Because this function doesn't have a nice antiderivative. So that's reason number 1 why we're doing this. We're coming back to some approximation techniques. Okay? Not all functions have nice antiderivatives. Okay? The second one is something that we won't really do in this class, but let's say you're in a science class, whatever that is. Science class. And in science classes, what do? You do experiments on people. No, experiments, right? On things. And so what do you do after you do experiments? You collect data. I don't know. This is why I became a math major, because I did not have fun in labs at all. So, assuming that, again, in a lab, okay, you do experiments, you collect data, and what does the data do? Well, it should tell you something. So you use all your data and you come up with a model, and let's say you have come up with a function that models your data, and you want to integrate that function. Well, sometimes that function, again, might not be very nice to integrate. You might have this ugly looking function from your data. And so if you're trying to figure out the integral of your data, or of the function modeled by your data, right, you might not have a nice function to integrate. So again, what do? Use these approximation techniques to find the values of the integral. Does that make sense? So I'm trying to convince you why we care about this technique. As a pure mathematician, I could care less about approximation. But over the years, I've become more and more convinced that, yeah, approximation is a good thing. Because all of these techniques we talk about, right, only work, right? All the things, all the theory you talk about in physics, for instance, only work what? If you don't have air resistance, if you don't have friction, if you live in a perfect world where nothing bad happens.
If your cow is spherical.
If your cow is spherical. Right. That's not generally the case, right? So in this case, FTC only works when you can find an antiderivative for your function, which isn't always going to be the case. Does that make sense? That room is so distracting. Okay. So what I like to do today is to basically talk about two other approximation techniques. So we've talked about these two already, so hopefully all of you are good with that. Again, it's the same thing from 5.1. The two other, actually three, we have three other approximation techniques. First one is called the midpoint method, which the name is pretty straightforward, I think. The second one is called the trapezoidal method, which would give you a hint as to what we use to approximate. And the third one, I'm going to call the Homer J. Simpson's method, also known as the Simpsons method. Homer J. when I made up. Obviously. Okay, so let's talk about the midpoint rule. So the midpoint rule is pretty straightforward. Yes. No, sorry. Okay. The midpoint rule is pretty straightforward, right? So instead of using the left endpoint approximation or the right endpoint to approximate, what do we use instead?
Midpoint.
We use the midpoint, right? So if you look at the third example here, right? So the height of each rectangle isn't given by the left endpoint or the right endpoint. It's given by the midpoint of each subinterval. So again, the setup for the midpoint is still the same. You divide your region up into n number of rectangles. Instead of using the left and right endpoint to approximate the height, or to evaluate the height, you use the midpoint to evaluate the height, and then you get your rectangles that way. So if you compare the three examples here, here's the left endpoint, right endpoint, midpoint, and it's trying to approximate the same thing, right? Using four rectangles. Which one appears to give you the best approximation?
The midpoint approximation?
For this particular function, looks like the midpoint looks better, right? Okay. Does that make sense? Okay. So if I look at this formula, let's see if this makes sense to you. So we say that the midpoint rule is given by this formula. Let me write that down. So we say m sub n, so m stands for midpoint, n stands for the number of rectangles, is delta x times f of x1 bar plus f of x2 bar all the way up to f of xn bar, where I say that x sub I bar is equal to 1/2, what is that, x sub I minus 1 plus x sub I. So let's do an example. An example I want to do is something we don't really need. An example where we don't really need to use the approximation, but I want to just do it as an example. So the integral from 0 to 2 of e to the x dx. So e to the x squared, you certainly need to use an approximation technique. E to the x, you don't. You can actually get the exact value. Okay. So let's use this function, and I want to apply this the midpoint approximation to this. So first of all, I need to specify how many rectangles to use, right? So I'm going to use 4. So e to the x looks something like this. It's an exponential function. And I want to evaluate the integral from 0 to 2. So the idea is I want to figure out what that area is, right? Now, without doing much work, what's the actual area? So what is that area equal to? E squared minus 1. How did you get that? Antiderivative of e to the x is e to the x plus some constant, so you can evaluate that between 0 and 2. So plug in 2, you get e squared. Plug in 0, you get 1. Subtract, so you get, that's by FTC, right? So in this particular case, you would not use any approximation technique to find the exact area, because in this case, FTC works. Okay, so, but I'm going to use this to, again, try to approximate and see how accurate these approximations are. Does that make sense? Okay, so for n is equal to 4, I want to use a midpoint approximation to approximate this area, even though I already know what the exact area is, right? So, in real life, whatever that is, you're going to apply this to not to a function that you can use the FTC on. So you're going to apply this to something like e to the x squared. Does that make sense? Okay. So to apply the midpoint approximation with 4 rectangles, I need to figure out, okay, what are the endpoints I use? So the first step is, just like before, you want to figure out what your delta x is, right? So what's delta x for this example? So we're going from 0 to 2, so delta x is going to be the width.
Be 1/2.
So how do you get 1/2?
It'd be b minus a divided by n.
Yeah, so it's going to be b is 2 minus 0, so 2 minus 0 over 4, right? Which is 1/2. So my endpoints is going to go from 0 to 2, so it's going to go from 0 to 1/2. To 1 to 3/2. Okay. So far, so good. Now, if I were to use the left endpoint approximation, I would use the left endpoints to find the height of my rectangle. If I were to use the right endpoint approximation, I would use the right endpoints to find the height of my rectangle, right? But now I want to use the midpoint approximation. So I'm not going to use my left endpoint, nor am I going to use the right endpoint. I'm going to use the midpoint. Right? Okay, so now you have to figure out what are your midpoints. So what do I mean by midpoint? It's going to be the midpoint within each subinterval. Okay? So what's the midpoint between 0 and 1/2? 1/4. What about between 1/2 and 1? 3/4, right? Halfway between a half and a 1 is 3/4, right? And then keep going. You probably see the pattern. What's the next one?
5/4.
5/4 and
7/4.
7/4. Okay. So the midpoint approximation so m sub 4 is going to be delta x times f of 1/4 plus f of 3/4 plus f of 5/4 plus f of 7/4. to do 1/2. F of 1/4, we're going to plug in 1/4 into our function. So it's going to be, what's my function? This is f of x, right? So it's going to be e to the 1/4 plus e to the 3/4 plus e to the 5/4 plus e to the 7/4. That's a lot of fourths, right? So plug that in, and I got approximately equal to 6.32. You can type that into your calculator. Now the actual value is equal to e squared minus 1, right? That's what you guys told me before. Plug that into your calculator. You get approximately 6.389. Approximately, because it's going to go on forever, right? E is an irrational number. Okay, so compare these two numbers. This is the actual value you get. This is the approximation that you have. Okay, what do you think about the approximation?
We're dang close.
Kind of close, right? Is it exact? No, obviously not, right? There's going to be some error. So the error is going to be the difference between the two, right? So what's the error? 0.0 something, right? The difference between those two numbers would be your error. Does that make sense? So your error, what do I have? 0.069. Or the absolute value of your error is going to be about 0.069, or the difference between the two numbers. Is that okay? So again, whenever you do approximations, right? It'd be nice to know how far off you are. Okay, and we'll talk a little bit about error bounds a little bit later on. When you take, or if you guys take Taylor series with me next year, okay, one of the things we'll be doing is we'll be approximating values of functions using Taylor series. Whenever you do some approximation, you want to know what your error is. Okay. For this particular problem, you know exactly what your error is going to be. Why?
Because we know the...
You know the actual value of the integral you want to calculate. Okay. Usually you don't. And so one of the things I will talk about a little bit later on, maybe tomorrow, is what is my error bound going to be? Right? What's the biggest error that I can get using a particular technique? But that's a little bit later on.
Good guess.
Does this make sense? Okay. Do you like this? Much different than trig sub? More importantly, is you understand how to use this, where it comes from. Again, essentially midpoint, all literally is use the midpoint. The setup is still the same as the left and right endpoint approximations. Again, you have to divide the interval up into the number of rectangles, and then instead of using the left and right endpoints, use the midpoint instead. Straightforward?
Yeah.
Good. Okay, technique number 2.
Trapezoidal.
Technique number 2 is something called trapezoidal, and it shouldn't surprise you that the technique, that the geometric interpretation of the trapezoidal rule is, instead of using rectangles to approximate it, you're going to end up having trapezoids. You guys know what a trapezoid is? That's not supposed to make you feel dumb or anything. I'm serious. Everyone okay? Know what a trapezoid is? Right? Okay, so you have like two bases, different base. Okay. Trapezoid, I think of it as
It's like a tent.
a 10, but it's like a rectangle with two
It's like a cake with saran wrap on it.
I'm sure okay, sure.
It's deep.
I'm sure I can have a conversation with your dad about trapezoids.
Very long
Like, for like hours and hours and hours. Did he show you the app, the website I showed him yesterday, the 3D grapher thing?
No.
Ask him about it. He was very fascinated by it yesterday. So, trapezoidal rule essentially is you're going to use trapezoids to approximate our areas, right? And so, where does a trapezoidal come from? It actually comes from a pretty